Good afternoon, everyone. Good afternoon, everyone. Good afternoon, everyone. Hi. Good afternoon, everyone. I, Ashna Chaudhary, feel gratitude to stand here before you today as a member of the Economics Association to extend a warm welcome to our esteemed guest, Professor Deepika Goel, who has joined us for today's pedagogy workshop on the econometric subject. In the world full of economics, econometric plays a crucial role. It provides the quantitative tools to test theories, build models, and share policies decisions. On that note, I would like to take this opportunity to welcome our distinguished speaker, Professor Deepika Goyal. Professor Deepika Goyal is a professor in the Department of Economics at Aryabhatta College, University of Delhi. With an extensive teaching career spanning nearly 28 years, she has been deeply engaged in undergraduate and postgraduate education, fostering academic excellence and research oriented learning. She completed her bachelor's in economics from Hansraj College and pursued her master's, MPhil, and PhD from the Delhi School of Economics, University of Delhi. Her scholarly expertise lies in microeconometrics, time series analysis, and forecasting, with a keen interest in applying quantitative methods to economic modeling and policy analysis. Her recent research explores critical issues at the intersection of macroeconomics and policy analysis, focusing on financial inclusion, macroeconomic determination of variables such as inflation and exchange rate, and climatic change, and the economy. Recognized for her expertise in economic methodologies, she has been invited as a resource person for specialized workshops mentoring students across various universities. Beyond her academic responsibilities, she plays a pivotal role in institutional governance and quality assurance. She is an active member of the International Quality Assurance Cell and serves as the coordinator of the NAC Cure community of Aryabhatta College, contributing significantly to strategic planning and acceleration processes. It's our honor to have you with us now. I request Dr. Bijoyta Yonzan to please facilitate now. We would now take an opportunity to thank our principal ma'am, Professor Swati Pal, who could not join us here, but in the brain behind organization these enriching sessions on pedagogy each semester. I would now like to welcome all the other members of Economics Department for this session. With this, I invite Professor Deepika Goel ma'am to take over.
So he has to be academically competitive in the college at the same time enjoy the college life, right? So, but we don't know in what manner he's going to fit into that particular scenario, right? So we say that this random variable is a college student XC, and we really want to know. We are always interested in knowing how is as a teacher, what kind of a characteristic does this student have. So a school teacher would want to know the characteristics of this excess. Okay, so it's kind of a descriptive statistic that the teacher would have for the student. Okay? Let's say what is his mean height, mean score, okay, or his average teaching time, his learning time in school. How much time does he devote to a subject at home? Okay, so mean of that, variance of that, right? So primary characteristics are mean and variance, and secondary characteristics, skewness, cutoffness, whatever. But this student, when the student comes to, because there's a difference. In school, the student had been there for about 11, 12 years. Okay. So over time, teachers and the school fraternity starts getting to know what that kind of a student, that person, that chap is. But in college, the student has just entered. We are just facing this new student. On the very first day, we start bombarding them with the concepts of micro, math, statistics, etc. Okay, and they really don't know how he's going to take it over the entire semester and then the next 3 years or 4 years. So then if you want to find out what is the average time that you want to devote himself to study, or what is the average time that he should put into statistics, okay, so that he fares well in statistics, becomes an unknown thing to us. Okay, because we don't know the behavior of the student. And hence the concept of expectations. Okay, so we say time, okay, that the student is supposed to put into this particular paper should be this, right? And the concept of probability becomes very prominent. Okay? Because probability acts as a tool which helps us to analyze the values of unknowns. Okay? So we get to know the probable value. Obviously, we are not getting to know the exact values, but the probable values, or sometimes we also call them like approximate values. Okay? So probable values is what the probability tells us, and then using this concept of probability along with this random variable, we also use the concept of expectation. So expected mean, using the concept of expected mean, what is the variance of this random variable is, and likewise, we can also have the concepts of skewness, kurtosis, expected values of all these can be found out. So that's how a student tends to relate himself that now this random variable. So we were in a world where we knew everything. Okay, data was given to us and we had to calculate mean. Summation xi is mean, right? But here we don't know what the values are. Okay, so we still are in the process of knowing the values, and hence probability that way becomes very important. So if we don't know probability, if we don't know probability, we cannot use the concept of expectation, and hence the concept of random variable, will not stand any meaning sense. So even till the second month or the third month of the first semester, sometimes students don't tend to relate to this concept of unknown. Okay, they still tend to remain in that word कि mean तो हम ऐसे निकाल लेते हैं, हमें ऐसे क्यों निकालना है, right? So probably if you start infusing into them from the very first day that everything is unknown, everything is unknown, everything is unknown, right? A random variable. So this concept of random variable helps them to identify that now we are living in a world of unknown. Okay, we don't know this. Okay, and we have to ascertain their values using the concept of probability. Okay, so that's usually the concept of random variable that I have been successful in communicating to the students, to a large extent. Okay. Now, another thing is sometimes students ask me, so till this point, the students are very clear with why are we doing chapter 1 and 2 of Devo. Okay. Then the moment probability distribution starts, okay, then they again start asking the concept, and I was just talking to Ritik or someone else also. The students ask me, what is the applicability of this, in the real world? Okay. So this probability distribution helps us to give a kind of a functional form to our value, our knowledge of the values of that random variable, okay, and the associated probability with it. Okay. So this probability distribution is kind of a pattern that a student has been behaving like this in the class for the past 2, 3, 4 months now. So I can now draw a kind of a curve, okay, to ascertain that if I teach for 2 hours statistics in a day, that's how he's going to behave. If I teach statistics only for half an hour, this is how he's going to behave. If I give an assignment today, that's how he's going to behave the next week. If I've kept the CA today, that's how he's going to behave the next week. Okay, or let's say in the coming month, right? So that basically helps me trace the pattern or the behavior of students in those few days that I have met him. So that's basically giving me probability distribution. Okay. The next question that they usually ask me is, why are we doing normal, binomial, क्यों करना है? Why do we know this? Why do we have to do this? Okay. Then I always tell them that for a teacher, there's always an ideal student in class. Okay. So as a parent also, as a teacher also, we always tell our students इसकी तरह बने. Try to be like him. He's so sincere, she's so sincere. Try to be like him, right? So अब हम अपने इस पैटर्न को जो हमने प्लेस किया है, उसको हम कह रहे हैं try to be like normal. Okay, this is our ideal boy. The normal distribution is our ideal boy. We want you to see how close are you to this, right? Or binomial or Poisson, whatever distribution that we're talking about. How close are we to these distributions? Okay, so if we are farther away from this distribution, study the pattern that we are interested in becomes a little difficult, because we then go to the non-parametric world. Okay, if we are close to these distributions, we are in a parametric world, because we then know what is the mean, what is the variance. Binomial का pattern follow कर रहे हैं, तो mean NC होगा, variance NPQ होगा, and so on, right? Or as a matter of fact, normal. communicate to them. Okay. Now, another concept which probably we don't do in the first semester, but in the second semester I'll come over to that a little later also. But for the beginning, is again basically testing of hypothesis. No, students generally don't relate to why are we doing this testing of hypothesis. What is that we are doing? So first of all, it is important for us to tell them that we are doing this because we are living in a world where population as such is going to have a
have a
master
master
data
data
set
set
of
of
something.
something. Okay,
So
so
that's
that's usually
not
not
given to
given
us.
to us.
So
So
like
like we are living in an
unknown
unknown
world,
world,
populations are
populations are
also
also
unknown,
unknown,
right?
right?
Okay,
So
if
if
you
you
want to
want to
study
study
something,
something,
you
if you
want to
want to
know
know
something.
something,
Now
now
you know
you
what
know
a
what a
random
random
variable
variable
is.
is.
Now
Now
suppose you
suppose you
want to
want to
know
know
how
how
many
many
economics
economics
honored
honored
students,
students,
tend
tend
to
to
go
go
to give
give
their
their
CAT
CAT
exams.
exams.
Let's
Let's
say
say, suppose
that's our
that's our
research
research
question
question
in
in
mind.
mind.
तो
तो
तुम
तुम
किस
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 को
को
पढ़ोगे?
पढ़ोगे?
Who
Who
all
all
will
will
you
you
approach?
approach?
Will you
Will you
only
only
approach
approach
new students?
students?
Will you
Would you
also
also
approach
approach
students who
students
are
who are
living,
living,
who
who
are
are
doing
doing
their
their
economics
economics
honors
honors
or
or
graduation
graduation
in
in
economics
economics
from
from
any
any
other
other
university?
university?
Would they
Would they
only
only
be
be
students
students
in
in
Delhi?
Delhi?
Would they
Would they
also
also
be
be
students
students
outside
outside
Delhi?
Delhi?
Would they
Would they
also be
also be
students
students
outside
outside
India,
India,
right?
right?
Or
Or
anything else,
anything else, right?
so
So
then
then
you
you
don't
don't
know
know
what the
what the
population
population
is.
is.
So
So
populations
populations
are
are
usually
usually
not
not
seen,
seen,
right?
right?
But
But
you
we
know
know how to procure a sample out of a population. Sampling tells us that. Okay, so once we know कि हमें कौन सा strategy लगा के sampling करना है, एक population में से एक sample उठाना है. Okay, so we can pick a small sample out of the population, small or big as per our requirements, and we can do the same exercise that you want to do on that sample. Okay, and that sample is going to give you information about the population, but we have to assume this, and economics is all about assumptions. We have to assume this, that this sample represents our population well. Okay, so if we know that our sample represents our population well, we can do this exercise of picking up a sample from a population and okay. So we can do this exercise of picking up a sample from the population, and all the sample unknowns will help us to decipher the population unknowns. Okay, so this exercise of conducting sampling, okay, is a very important thing because of the fact that populations are not seen, populations we don't know. Now, when you say that I wanted to know the average number of students who appear for MBA exam after having done economics, and let's say that turns out to around, let's say 1,000. Suppose that's the number. That's the mean that you get. X bar is 1,000. Okay. Can you say that this is also mu? Okay. Can you say that this is also mu? So that will be a different thing. Okay. That will be a difficult thing to say. Why? Because if you have not conducted your test, okay, so then, so it's something like this, that you've made something in the factory, and before selling it out in the market, you will have to do a test, okay, that whether this is workable for the group that I have manufactured it for, right? So it's the same kind of a strategy that one follows for testing of hypothesis also. Okay, so every test helps us to connect this disconnect of how a sample represents a population well. Okay, so if the test is successful, we say that this sample represents our population well, and hence, we can say that our null hypothesis, if suppose it is this, okay, then we can, satisfy this, but given some error, okay, which is what alpha is. Right? So we cannot completely say 100% kabhi bhi koi statement ko hum confirm nahi kar sakte. There'll always be some element of error involved in it. Okay, so this is what I do about random variables. Okay, so before moving on to the central limit theorem, for that I have to show you the Excel sheet. The next concept is probability distribution that I usually deal with in the class. The presentation only. The presentation only. Yeah. Okay. So here what I have done is that I have just listed down some common, points about each distribution. So if a student has to remember that what am I talking about, okay, and what distribution is what. So these are some quick answers that one can get on each of the distribution. So uh, let's say the first is binomial, okay, which all students usually relate to because they've done it in school also. But then let's say the scenario is that suppose a student guesses on 10 true or false questions, and each guess has a 50% chance of being correct. Okay, so our random variable in question is number of correct answers out of 10. Okay, so I know very quickly that I have to apply binomial distribution where x follows binomial with n 10 and probability of success is 0.5. So then I can quickly ask them what is the probability of exactly 7 correct. हम formula में PMF में S7 की value डाल देंगे. And you can also extend this concept to expected value, variance, NP is expected value, variance is NPQ, and so on, right? So these are some of the common things. I'll also come on why, which distribution to pick and why. Next, please. Next is Poisson distribution. Okay, so the example that I usually give is calls in a call center. Okay, so a call center receives on an average 3 calls per minute. The random variable is number of calls in the next minute. Okay, given the information that a call center receives on an average 3 calls per minute, random variable is this. The distribution is Poisson with lambda equals to 3. And what is the probability that exactly 5 calls come in the next minute? So that is something which one can easily relate to, put the value of that in the formula and get an answer. Okay. Then you can also have extreme questions like what is the probability of 0 calls, okay, which is e raised to power minus 5. Yeah. And Poisson is usually used for rare or random arrivals, okay, for rare events or random arrivals. So this is something you have to tell to a student about a Poisson distribution because that distinguishes it from other distributions. Next. Okay, hypergeometric. Here we are drawing without replacement. Okay, so let's say the scenario is that a box has 20 balls, 5 red, 15 blue. A student draws 4 balls without replacement. Random variable is number of red balls in the sample. So X is number of red balls in the sample. X follows hypergeometric with N20, K5, N4. Okay? I think in your book it is capital M and small n, right? So you just replace that values there. And you just put that down in the formula. The interesting thing here is that we can use, sometimes I do that in the class, that we use real objects, okay, like pens or stones, okay, to tell them the idea of what is without replacement. Okay, that what do you understand by without replacement and with replacement? Okay, so that's like important because if suppose you have a population, if you have a sample size of let's say 10 and you have to pick up samples of 2 each, okay, from that population. So what is the strategy with replacement and without replacement? How many samples can you derive? So that is something that students don't relate to unless they've not done permutation combination earlier. Okay, so for doing that, sometimes these real-time examples help, right? So just start with 5 pens, okay, and then start teaching them that, if without replacement uthane, do uthao, or with replacement uthane. Okay, then how many samples will you get? So that's something very interesting that students usually relate to. Next, please. Okay, so geometric distribution, we don't do at length in our classes, but definitely Devo does talk about this. The geometric distribution says, probability of the first success. Okay, the scenarios, let's say, is rolling a fair die until a 6 appears. Okay, so that's the easiest example you can teach them. Random variable becomes number of trials until the first success. The distribution is geometric with p equals to 1 by 6, and probability first success is on trial k is 1 minus p raised to power k minus 1 p. So that's the basic PMF of a geometric distribution. What is the probability that you will need at least 3 rolls to get a 6? So 5 by 6 raised to power 2. So just substitute the values in the formula and you will get it. But this distribution is unique because it tells us waiting time until success. You can't stop until success has been delivered, okay, or you don't get success in that particular event. Okay, now the interesting part is that how do you explain all the 4 distributions to them, okay, with just one example? right? So one example, 4 distributions, that is what a challenging thing to do. So let's say the scenario here is a jar contains red and blue balls. Students draw balls and record the outcomes. Okay? So I have never done this in the class, sorry, but this is the example I usually give them. Okay? And they relate to it easily because it's an easy example to do if they, even if they want to do it. So where will binomial come into picture? If each draw is independent with replacement, or if there is a very large jar, okay, then you know that you have to apply binomial. Okay, what's the probability of exactly getting 3 reds in 10 draws? Okay, so distribution will be binomial with n10 and probability of success whatever is given to us. Okay, so P. When will it be hypergeometric? For the same example, if each draw is without replacement from a finite jar. Okay, so if the jar is finite, okay, then if each draw is done without replacement, then that automatically will imply a hypergeometric distribution. Okay, so I can ask the question, what is the probability of getting exactly 3 reds if we draw 10 balls from 50, where 20 are already red? Okay, so that's exactly a typical example of a hypergeometric distribution. And you know it's hypergeometric with N50, K20, and small n as 10. Poisson. If probability of drawing a red is very small, but we make many draws, okay, so you are actually applying Poisson approximation to binomial with lambda equals to NP. Okay, so we are saying suppose the jar is huge with only 1% red balls. Suppose the percentage of red balls in it are very small, but then the number of draws that we do are very huge. Okay, they are very large. What's the probability of 5 heads? So we immediately know that this is Poisson approximation to binomial with lambda equals to LP. Okay, that's how you approximate Poisson to binomial. And when it will be geometric, if we keep drawing until the first red appears. So it's a waiting time until the success happens. So what's the probability that the first red appears on the 4th draw? So we know distribution will be geometric with probability of success as 3. Okay? So this is how, with one example, you can actually link together 4 different distributions and you can tell them that that's how you have to go about it. Okay. So I understand that with the first go, the students will not be clear with these concepts also. Okay. So this is not as simple as we want to be. But then, having to deal with a book like Devore, you cannot just go down completely to a plain language where the essence of what we are doing goes away. Okay, so this is how I try to knit up things, giving single examples for various kind of a situation. Okay, how do students decide about what distribution to use? So these are some of the questions I usually ask them to ask themselves. Is the number of trials fixed or random? Okay, so if it is fixed, it could be either binomial or hypergeometric. If it is random, then it could be geometric because you're talking about waiting time until success happens. Is the sampling with or without replacement? If it is with replacement and it's a large population, then binomial. If it is without replacement, then straight away it is hypergeometric. Is the event rare with large trials or continuous rivals? Then yes, it has to be Poisson. Okay, so these are some of the questions which one can ask. Okay. Then coming up to continuous distributions, I've just taken the 3 continuous distributions which we do in our syllabus: uniform, normal, and exponential. So what is a uniform distribution? All outcomes in an interval are equally likely. So again, like this, by giving them snippets like this, they would be able to retain things in one go. Okay, not like if you give them a lot of definitions, lot of formulas, so students tend to get lost. Okay, so these are like main features, main snippets about a particular distribution. What example? The best example that one could give is the bus arrival time. So that's the easiest example to give. Suppose the bus comes every 30 minutes, but you arrive at the bus stop at a random time. Okay, so your waiting time is uniform over 0 and 30 minutes. Probability you wait less than 10 minutes, 10 upon 30. Okay, that's the simplest thing. How can you make it more accessible to students? Just draw a rectangle with a constant height PDF. Okay, we know what a uniform is. So it's something like this. Right? a rectangle with a constant height PDF, okay, and it shows equal likelihood of all being selected under this, right? So that's the simplest way in which you can explain uniform. Normal. So I think all of us know normal, and we've made it so simple by knowing it more and more. Okay, so it's a famous bell curve, common in nature and measurement. Okay, that's the simplest way one can define a normal distribution. What is an example? The heights of students in a class, student heights are roughly normally distributed with a mean of so and standard deviation of 10 centimeter. One can ask the question, what is the probability a randomly chosen student is taller than a certain value? So we know how to go about it. Standardize, use the Z table, find out the probability. Okay. What we need to emphasize here in normal distributions is symmetry. Okay. And the 68, 95, 99 rule. What is the 68, 95, 99 rule? The students here, you've done stats. What is the 68, 95, 99 rule? Okay. This has to do something with variations. Okay. Yeah. Now telling them. 60% of observations lie under mu plus minus 1 sigma. 95% lie under mu plus minus 2 sigma. And 99% lie under mu plus minus 3 sigma. And that's why it is symmetric. Okay, it is spread. Okay, that's why it is normal, bell shaped. Okay, this particular feature gives it the shape that it requires. Okay, so that's a feature of normal distribution. What is exponential? It models the waiting time between independent random events. So it is very much connected to Poisson. Okay, because in Poisson we're looking at the time, the probability of the next arrival. Okay, but here we are talking about waiting time between arrivals, right? So therefore, Poisson and exponential are related to each other. The example that one can give is again a call center example. A call center gets 5 calls per hour on average. Waiting time between 2 calls follows exponential with lambda equals to 5 per hour. Okay, so you can just put down in the formula and calculate the required probability. What needs to be emphasized here is the memoryless property. Okay, that probability of waiting 10 more minutes is the same no matter how long you have already waited. Okay, so it does not carry anything of the past, right? So it just tells you that this is how it is. You have to wait for it for 10 more minutes. For the same pattern will be there whether you wait for 10 more minutes or 20 minutes, it will be the same pattern. Okay, so that's what the memoryless property is. So here I've just drawn these 3 graphs: the uniform, the normal, and exponential. The best part is that these kind of curves, if you people are proficient in some software, R or Python, okay, you can draw such graphs there, because these softwares helps you to play around with data. Okay, so this particular thing, so I actually feel that statistics should always be taught along with the software, because it tells you, it portrays, it displays, how can you play around with data, and how can we get, some intuitive ideas out of it. Okay, can you please go to that Excel sheet, the central limit theorem? And just go to sheet 1 for now. Okay. Now, the other very important concept of central limit theorem, which by definition students relate to, okay, students understand also. But if you were to see it visually, okay, then it's always good to see it visually how it happens, especially with changing samples, okay, or changing sample sizes. Now, in this, the first column, what I have done is I have drawn a column of random numbers, okay, using the random number generator command in Excel, right? So I think I have drawn about 900 or 990 numbers, something like that. And on the top, this 503.1525 is the population mean, right? All of you know how with the data we can plot a frequency histogram out of it, right? So just give some upper values to the bins. And along with that bins, you just derive the frequencies and draw a histogram. So that population histogram looks something like that on the right-hand side, right? And this is almost like a rectangular thing. Okay? It has a rectangular kind of a shape. Now, if I want to see whether this particular data follows CLT or not. So what is CLT? CLT basically tells us that if your population is normally distributed and you draw a sample out of it, so that sample will also be normally distributed. But what happens if a population is not normally distributed? Okay? So if it is not normally distributed, then the sample will automatically be normally distributed as the sample size increases. Okay, so large sample basically means n greater than 30 or so. Okay, so what I've done is that on the right hand side, you will see I have drawn some samples. Just go below. Yeah, this one. I have drawn 10 different samples of size 30. And on the left hand side, I have their means, the sample means. Okay, for n equals to 4, that's column C, C32 to C41. Yeah. And the second is for n equals to 10. And the third is for n equals to 30. Okay. Now, with the random number generator, there is a slight problem because it keeps on changing. Moment you click on your Excel sheet, the sample changes. Okay. So what happens is that I've fixed it. Okay. Just to see how the things can be done. But if you don't fix it, the real fun is there. I'll show you that sheet also where we have not fixed it. So there are sometimes certain errors also, but then you actually get to see what you see. And if I now plot a sampling distribution of all these samples, okay, so that's given up from D, E, F column, E, F, G column from 5 to 24. Yeah, here. That's the frequency distribution. Now here, this frequency distribution is of the sampling means. Because what I'm saying here is that the sample mean. So here when we were asking the question, does X bar follow mu? Okay. So or does value of X bar can be said as the value of mu? That only will happen if the CLT is applied. Okay. So therefore I want to know the distribution of the sampling means in question here. Okay. Now this graph, if you were to plot this n equals to 4, 10, 30, just draw a line diagram of all of that. Just go to sheet 3. And just a little below, there is a histogram of sampling means. You will see that as the sample size is increasing here, because of, see, what happens is that when you do a random number generator, the Excel sheet sometimes starts showing you errors because you will see at some places there is this reference error kind of a thing. Why? Because every time the number changes, and I have put in formulas here. So these all these formulas have references. Okay, so it becomes a cycle kind of a thing. This cycle breaks when a moment I change the values. So I would actually encourage you and your ma'am to do something like this with them in the class and make them work, make them draw this kind of a histogram, because this actually gives you a visual idea of a central limit theorem, right? Yeah. No, so what we do is that for some of the classes that that I want to do a practical on, I either ask them to get their own laptops, or if we get a computer lab free, we do it there. But we don't do it every time in the class. Okay, so I just designate some classes where I can do a practical component. And then I think nowadays most of the students have their own laptops. So they prefer getting one. Why? Because they can also store work in their own systems rather than doing it on a college system. Okay. And in past, I've also done it on an online, in an online mode, right? So where a system is accessible to them. So just to give them an idea of how things work. Okay. In the same sheet, can you please click on binomial versus normal? Sheet binomial versus normal. Yeah. This is again an example of normal approximation to binomial distribution. okay, with continuity correction. So I have not procured data from anywhere. It is just a random data that I am using. Okay, so that makes life a lot more easier. You just work with random data. So here I had number of trials equals to 65. Okay, and I have also plotted them down here. Okay, so this 0, 1, 2, 3, 4, 65 till 65 numbers I have for binomial distribution. And this binomial PMF just comes with this command, which is binom distribution. It's a simple command in Excel where you just say equal to binom dot distribution. Okay, and then just give its particulars. What is the number of trials? What is the mean? What is the variance? That's it. Okay, and you just say enter and you get this entire column filled. Okay, just copy it down, you fill it up, right? The next is normal approximation, where I actually use the formula. If you remember, we also have this continuity correction formula, right? Which is also given in the board. So that formula I've just translated into a formula in Excel and got the desired values here. Okay. So if now you would see, I wanted to show this, but can I come here and show this? Here, these bars curve is not right. We don't get this down. I keep increasing my curve. More I take increases see makes telling students with some numbers, okay? And we don't really need to know the software or Python or Stata or whatever. I mean, even a simple Excel would do the job. I think which most students are comfortable with and they have it. Okay, that's the best part. Okay. Just put the presentation. Slide 14. Yeah. Another concept which really requires a little bit of uh, talking about is the concept of type 1 and type 2 error, right? So usually students don't get it in one go. So the kind of examples which they can relate to, okay, helps them to understand this concept. So we say that type 1 error is the probability of rejecting null, okay, when the null hypothesis is true, and uh, type 2 is probability of not rejecting when it is false, right? Now, the example which, especially after COVID, I've started giving this example is that suppose you go for a test, okay, or COVID test. So you have COVID and you get it. Okay, that's the right thing. You don't have COVID, you don't get it. Two right things. But then there are two kind of errors that can also happen. You have COVID, but the test does not tell you. Okay, you do not have COVID, but the test tells you, right? So, let me just dot that. We say that reject and reject. Something which is true, you do not reject it. That's the right thing. something which is false and you reject it, that's also right thing. But then there are two errors which happen. Okay. So something which is true, you reject, that's type 1 error. Something false and you do not reject, that's the type 2 error. Okay. Now, when you go for a COVID test, okay, and you had COVID, but the test did not tell you, that's type 1 error, right? Second, you did not have COVID, but the test said that you have COVID. Okay, that's type 2 error, right? You can relate to it. Now, type 1 error is more serious. If you do not have COVID, but the test is telling you that you have COVID, what is that you're going to do? You're going to sit back at home, not, relaxing, 7 days fun, quarantine, whatever. Okay. But suppose you have COVID and the test tells you that you don't have COVID, you go out and contaminate others. Okay, you infect others. Okay, so which is more serious? That you don't have it, but you still sit back at home. So type 1 error is more serious than the type 2 error. So I think this is one example that students always relate to, especially after COVID, because they must have undergone COVID testing several times, okay, over past 5-6 years. So they understand that what is it that is happening there, and that's how they can explain type 1 and type 2 error. Another concept is the p-value, okay, probability value of a test, right? And so I have always seen that when students do their econometric projects, okay, and because we make students do some econometric projects, they have to run a model and they have to test the statistical significance of a particular variable, right? Now, the biggest aim, they have only two aims in that project. One, सबकी p value 5% से कम आ जाए, ठीक है, and the other is r square ज़्यादा आ जाए, right? So that everything becomes significant. R square is 90%, 99%, model is good, and you are done with your project. Okay, nobody is bothered about the interpretation that is coming out of the project, right? Now, I actually want to tell them that p-value is actually not nothing, has got nothing to do with statistical significance, because statistical significance comes with alpha, which is your type 1 error. Okay, p-value actually throws you kind of a surprise of how null is going to behave, right? So for this, just taken a small example, that suppose we want to test whether students can really tell the difference between Coke and Pepsi. Okay, suppose you don't have in two glasses you have both the drinks, but you don't label them as Coke or Pepsi. We ask 10 volunteers to taste blindly. Each must say Coke or Pepsi. They have to give one option, whether it's a Coke or a Pepsi. If they are just guessing, the probability of being correct is 50%. Okay, that 50% of the times they will say that it is correct. Okay, if it's Coke, it is Coke, it is Pepsi. If they say it's Pepsi, it's Pepsi. The probability of success is 0.5. So let's say we collected data, 8 out of 10 were found to be correct. But is it statistically significant? The graph below tells you it is not. Why? Because you see that the highest bar is that where P is actually your number of outcomes is 5. Okay, so in 50% of the cases, you have the maximum concentration. But then beyond 8, 9, 10, 8, 9, 10 are extreme cases. Because what I have got is 8 out of 10 are correct. So probability X greater than equal to 8, okay, becomes my rejection area, right? Extreme area, which is like this red bar. Okay, so this chart shows the probability of each outcome 0 to 10 correct if the null is true. Okay, and most outcomes cluster around 5 correct, because that's the maximum thing that one can get, 5 options correct. Chance of seeing 8, 9 or 10 correct purely by guessing, okay, that area in red is the p-value. So this is the p-value which comes out if you do the calculations, you put your binomial formula and do the desired calculations, the probability comes out to be 5.5%. Okay, and because 5.5% is more than the conventional 5% level, what happens? We do not reject the null. Okay, so that means your test is not statistically significant, which you thought it would be. Why did we think so? Because हमारे पास 8 जवाब ठीक वाले आए थे. ठीक है, so we thought the test is statistically significant, but it did not turn out to be. So p-value is just like a mirage. It only tells you how your null is going to behave under certain situations. Okay? And it does not tell you anything about the statistical significance of the test. Okay, Uh, just go to slide number 16. I think I'll just take up one last concept, and I will. Yeah, this one. Okay. So I wanted to do a lot of chart plotting in econometrics, but obviously there was, I mean, I will have lesser time here. So I just thought one would be enough. But if the students in econometrics are doing classical linear regression model and the basic assumptions of the classical linear regression model, so we all know that this heteroscedasticity assumption or the assumption of homoscedasticity is an important assumption, okay, whereby we just say that the mean of the error term remains constant throughout. Okay. Now, the more interesting thing is that mean of the error term never remains constant. If you work with the real-time data, especially cross-sectional data, mean of the error term, and I'll actually show it's not just cross-sectional. Any random data that you put in, there would always be some amount of variance in the errors present. Okay. Now, to show this, what I've taken up an example where I say that income is a function of spending. Okay. And I've just randomly assumed that spending is on average half of income. So spending is equal to 0.5 times income. So I've just randomly assumed this particular function. And my error term follows normal distribution with mean 0 and variance sigma square, where the sigma square is not constant now. It is changing with observations. Okay. And I assume standard deviation sigma is income by 5. Again, I just assumed it randomly, right? So actually what I'm saying that at low income, let's say income 10, my error is normally distributed with mean 0 and variance 4. And at high income 100, my error term is normally distributed with mean 0 and variance 400. Okay. So as the spread of spending increases, okay, the spread of the spending increases as income rises. Okay. That's what I'm basically assuming. Can you just go to the Excel sheet and the last sheet in that heteroscedasticity? Now the first column income, I've just generated using the random number generator. Okay, so it's not cross-sectional, not time series data. It's just simple numbers. Okay, that I've plotted ranging from 1 to 50. So some income levels I've created here. The next column is expected spending, where just simple formula is that spending is 0.5 times income. So just the first column multiplied by the second, and it gives me the expected spending, right? Now, because my error term has some variance which is not constant, which actually means that it's going to affect spending, right? So therefore, my expected spending should be this plus some amount of error into it, right? So if you just look at column E, what I have done here is I've done some amount of simulation. So what does simulation imply? That using my hypothetical data, I am just trying to bring out a trend, okay? And it's a huge population where I'm just picking one observation at a time, right? And so it's like one sample or one observation, one draw from the entire sample. And that simulation, that change helps me to prove my point, what I'm trying to do. Okay. But then it has to be doctored in a way, okay, that it does not look wrong, right? That's how a simulation usually works. So my observed spending, so this column E basically gives me a sense of error, okay? The error which I was just talking about, which is non-constant, right? And now if I add up 5 times in income plus this error, I get column F, observed spending. Okay. This observed spending, which is my column, which is my dependent variable, this is, I have plotted in a scatter plot here. Okay. This scatter plot has this trend line in between, which actually tells me what my actual regression is, right? And the points here tells me the actual value. So the fitted values is given on this trend line, and the actual values will be given beyond this particular trend line, right? Now, if I just simulate it, so what I mean by simulation, I just have to go there and show you. You will see that I have simulated this column in the sense that it's a 10 volts. For second ball, I get new set of 10 volts, multiple volts. You will see again, it starts with changing. They are not the same. Had they been the same, they would have been, but if they're not the same, then they would be showing a diverging. That's concept of econometric source statistics using numbers, don't data. Those are some data that much, and I'm just random sort of a formula, and the concept which is very relevant is actually in your regression, your classical regression model. Then you estimate that the okay, your interpretation is not the line. There will be some bias in your that's it was the same for medical linearity also and other put myself across to some extent. Thank you so much. Yeah, sure. So, it is something like when you, so how do I explain? So, suppose you have 10 balls with you, right? And I ask you to pick up one ball from those 10 balls. In the Excel. Okay, so that was जो ये window वाला sign है and F9. You just highlight that column, this tab with that window sign and F9. That gives you simulation. Yeah. Yeah. Right? That's how simulation is done. So this is actually very easy. It seems like a jargon that we are doing this and we're not getting across, but actually this is nothing. You are actually just playing around with your data. You're saying that in this normal distribution, errors are normally distributed. You had infinite number of observations in that continuous distribution. You're picking one by one, right? And just try to see that all those, how well do they fit in your model. Anything else? But yes, I think yeah. Okay. Know that we have this is very advanced age because they take to get appointment and but So actually, my idea is, Richika, that these concepts, even the students who are not who are average or who are below average, they relate more to it. Every student nowadays work on, do gaming, do work with pictures, their phones, chat GPTs, their all their social media apps. They're working with images. Okay. So they relate more to images. So these are not like a compulsory part of your evaluation. You do them as an extra thing. This is the first thing you tell them, that we are doing this as an extra thing. But by having done that, you will understand the concept fully, okay, or a little more than what you have just understood from the book. Okay? So I always try and substantiate whatever I can, with such exercises, or even not even working with Excel. Just simple, as I said, 5 pens, draw with replacement, without replacement. Because sometimes these are like fun activities. Things don't become boring with for them. On days they don't want to do that standard book and example and question, and so you say, okay, chalo, let's just see what with replacement and without replacement implies. So like once we did an exercise on sampling in college. Stratified sampling क्या होता है? We have 13 courses, right? हर course से एक बच्चा randomly उठा के लाओ, and we'll make a group. This is stratified sampling. Multi-state sampling क्या है? ठीक है? So these are the kind of things you don't actually need to. I mean, I don't say that my students completely involve themselves into this, right? And I get a lot of avoidance rate also, because they think that class is free. कुछ नहीं कर रहे हैं तो भाग जाओ, ठीक है, चले जाओ. But at the end, I feel जिनको पढ़ना है वो पढ़ेंगे, definitely. And जिनको नहीं पढ़ना, आप उनको force नहीं कर सकते पढ़ने के लिए, ठीक है? So by doing such things, you can just try and generate interest in them. Exactly. Because this is what students have started asking me, especially CUET के बाद, कि ये हम क्यों पढ़ रहे हैं? What is the applicability of this in real life? Right? So, I mean, that's it. Actually, देखा जाए तो advantage बहुत है, but it just depends on how much time you have, one, and how much students want to absorb. That's the. नहीं, तुम मत कराओ. अगर उनको ये कॉन्सेप्ट बर्डनसम लगता है तो मत कराओ. बट देन व्हाट इज द ऑप्शन? तुम बुक से कराओगे. बट अगर वो उनको नहीं समझ आता, अगर ये नहीं आ रहा, तो बुक वाला तो बिल्कुल नहीं आएगा. या या एब्सोल्युटली. Although Devore is a very good book, it's an excellent book to conceptualize. Yeah, to cover the concepts. But then, of course, we have a mix of, especially after CUPT, we have a mix of students. Oh, yeah. So I did this normal approximation to binomial exercise with my program students when I was teaching them statistics, and they really enjoyed it. Yeah, yeah, with X. So I mean, a day I just asked them to get there. I mean, it's a small class, 21 students only. I asked them to get laptop, and I said that कि अगर एक भी दो भी ले आएंगे, सब मिलके बैठ जाओ. You just have to see what is happening, and then